There we go. So today we welcome Alex Possajennikov from University of Nottingham to talk to us about unbeatable strategies in games. So over to you, Alex.
Okay, thank you, Jonathan. Thank you for the organizers of this seminar. As I put it on my slide, that is for the Learning Evolution and Games online seminar. I talk about games for sure. What I talk about will have some evolutionary foundations. There isn't that much about learning, unfortunately. So, but at least two of the three uh, words in the title of the seminar should be appropriate. Now, what I investigate is a very simple question. In a sense, what are reasonable manners of play in a game? Usually understood as strategies in a game. The standard concepts in game theory would consider good, reasonable manners of play as such that are better than other strategies in the game, which are then encapsulated in the Nash equilibrium concept. Player I would get a better payoff by playing Nash equilibrium strategy than any other strategy SI. Or further refinements of this concept, such as a dominant strategy, where player I would get a better payoff by playing a dominant strategy than playing any other strategy SI, or any strategies of the other players S minus I. Now, what I found interesting is also to look at the concept of reasonable manner of play as such that would make you get a better payoff than other players get. You want to get a payoff that is better than other players. This needs, of course, that their payoff are comparable. There is some common payoff scale. In evolutionary game theory, we often talk about evolutionary fitness as a kind of common currency that we can measure the success of players. So that is applicable. And what I will call as unbeatable strategy is such strategy as star for player I that would give player I a payoff by I higher than the payoff of any other player J. If player I uses this strategy as I star, and that holds for any strategies of the other player. Player I has an unbeatable strategy as I star. If the player I can guarantee that player I would always get a payoff not lower than any other player. That's what I would understand as an unbeatable strategy. It's not my term. I will explain who came up with this term. And what I investigate is then when do unbeatable strategies exist in games? And I will look at different variants of unbeatability and see which ones exist when. Perhaps to give an even more formal definition, and here is also the reference to the paper that introduced this concept that they call unbeatable strategies, a paper by Amir Yevstygnev and Potapova in economic theory last year. So we look at the games with a finite set of players and some strategy sets for each player and payoff functions for each player. That is more or less standard. And so what these authors call as unbeatable strategy, and I modify it slightly as to call it unbeatable-for-sure strategy, is strategy SI star that satisfies this inequality that player I gets a higher payoff, or not lower payoff than player J for any strategy combination of other players and for any other player J. Last valid point says more or less what I said. Player I's payoff is always not lower than that of any other player, not beaten by that of any other player. What these others didn't talk about, what looks like a natural extension, is to consider mixed strategies, which are then work on the probability distributions, delta S over strategy set Si. For finite strategy sets, these distributions are then vectors, sigma I, that sum up to 1. And we can then formulate expected payoffs of players. So this standard formulation of expected payoff with appropriate probabilities. And then a mixed strategy sigma I star of player I can be called unbeatable in expectation if it guarantees player I expected payoff not lower than that of any other player or any strategies of the other players. It's a more or less straightforward extension of the previous definition. The two mixed strategies. The difference is, of course, that it's now unbeatable in expectation. Your expected payoff higher, not the payoff in each realization. You may, for a particular realization of mixed strategies, get a lower payoff, but in expected term, you, player I, always get a higher payoff than player J.
That's right. This is non-trivial, right? Because by playing a mixed strategy, you can lower other people's strategies and make it hard for them to respond.
Well, yes, you extend other players' strategy sets to mixed strategies, and that makes it more difficult in one sense to have an unbeatable strategy. On the other hand, you can also use now mixed strategies, so that makes it easier.
Yeah.
So a priori, it's not clear how it will affect the existence results, but we'll see that it actually helps. If well, we are in a seminar on evolutionary game theory, so there are experts in evolutionary game theory concepts. Some of the names may be familiar to some of you. And in fact, so what I use as unbeatable strategy is this definition, that the payoff of player I is higher than the payoff of player J for any strategies of other players, either in expected terms or in sure terms. There was previously a concept of unbeatable strategy that Kojima introduced in 2006. I call it here unbeatable in quotation marks because the concept I use is rather different from the concept that Kojima had. Kojima's concept was an generalization of evolutionary stable strategy concept, so that these inequalities hold. Strategy SK he called unbeatable. If this inequality holds, strategy SK gets a higher payoff than any other strategy S for any proportion of the other strategy S that a mutant can play. Evolutionary stability, this inequality needs to hold for small epsilons or small proportions of mutants. Kojima extended this to an arbitrary proportion of mutants. Now, that is different from what I call unbeatable strategy because the concept I use is based on relative payoffs rather than absolute payoffs, as Kojima's definition is. And relative payoffs also were analyzed or used to argue for evolutionary foundations, starting from Schaffer's concept of evolutionary equilibrium, finite population ESS, and then also generalized or modified by Alois Ferreira and Anya to call weakly globally stable generalized ESS, which is characterized by this inequality that player 1, who uses strategy S star gets a higher payoff than player N that uses strategy strategy S, any other strategy S. And for any number of players that mutate from S star to S star still gives a higher payoff than S. So that is the intuition behind this definition. If some players mutate from S star to S, players that stayed in S star still gets a higher payoff than those who mutated. And therefore S star is, in some sense, evolutionarily stable, and that's what's called, Alois Freire and Nadia called weakly globally stable generalized ESS. Now, this is a necessary condition for what I call unbeatable strategy, because if this inequality for the weakly globally stable generalized ESS needs to satisfy for strategy combinations that involve two strategies, S star and S, a number of players playing S star and a number of players playing S. While what I call unbeatable strategy needs to hold for any strategy combinations S minus I. Doesn't need to be all using the same strategy. It could be any combinations of strategies they use.
Can I ask a question just for clarification? So are you assuming symmetric games? So because you say that everyone is using strategy as star, that supposes that everyone can use the strategy. So they're like in symmetric games,
yes,
that could be the case.
So that is, as I say here, so these definitions and this most of the concept in evolutionary game theory are for symmetric games, in which case what you say apply. I didn't yet restrict myself to symmetric games. In fact, I will mention that what I will be looking at for two-player games at least does not need a symmetric condition.
Thanks a lot.
Any other questions on this? I mentioned also here that there are papers now that try to induce evolutionary selection in an experiment by excluding those players or those participants who get the lowest payoff in a given round. So that is a paper by these authors. And I now have a project with Stefania Gao, who is also now at Nottingham, to similar lines, but that is not strictly related to what I've said. All right, so then kind of moving on to formal analysis. So here I mentioned explicitly that not necessarily symmetric games that I'm looking at. But I start the analysis with looking at two-player games, not necessarily symmetric. So in these games, an unbeatable strategy, we have only two players, only two strategies, Si and Sj. Unbeatable strategy is defined with weak inequality. One can also talk about winning strategy with strict inequality. Now let's then look now, instead of the game with payoffs pi I, for the two players, the game with relative payoffs, rho, which is the difference between the two players' payoffs. Rho I is from player I's point of view, rho J is from player J's point of view, which would be then simply minus rho I. So this transformation then transforms the original game gamma into a game delta, which is zero-sum game with these payoffs, rho I and rho J. That's what Amir et al. Also looked at, and they then state a proposition that if this game delta has a pure saddle point, pure equilibrium with certain value V, then there exists an unbeatable strategy that I call now unbeatable-for-sure for at least one player in the original game gamma. And intuition for the proof is in these two lines. In fact, if the value of the game is positive, then player I, using his equilibrium strategy, can win, can always get a payoff higher than the other player. So player I then has a winning strategy. It follows from the fact that pure saddle point, the minimax, works in this way. The player I can actually win, be always higher than the other player if V is larger than 0 from player I's point of view. Correspondingly, if V is smaller than 0, the player J has a winning strategy. Of course, if V is equal to 0, then each player playing the equilibrium strategy can guarantee 0 in terms of relative payoffs for him or herself. Then Amir and Stigneyev also looked at extensive form games, finite perfect information game, extensive form game, a game without information sets, then has a pure strategy subgame perfect equilibrium, and in which case then at least one of the players has an unbeatable-for-sure strategy in that game. Okay, so this was the result in Amir et al. Paper, and then the extension of it to mixed strategy is again relatively straightforward. If the game gamma delta, the relative payoff game, has a mixed equilibrium, which may be mixed, then there exists an unbeatable-in-expectation strategy for at least one player in the original game gamma. And the reasoning, the intuition for the proof is similar. So we look at value of the game. Now it's in expected terms, since equilibrium can be mixed. Expected value of the game, EV. It is same in any equilibrium of the relative payoff game, since the game is zero-sum, so it is well defined. And the sign of this value then tells us which of the players has unbeatable in expectation strategy. Either both of them, if the value is 0 in expected terms, or one that has the positive value from the game, and it has a winning strategy. So that is, I perceive as relatively straightforward extension of what the other authors did. And then a further extension that most of you probably already realized, that we know a sufficient condition for a game having a mixed Nash equilibrium is that it is a finite game, and therefore in any finite two-player game, gamma, not necessarily symmetric, no further condition other than being finite two-player game, there exists a strategy that is unbeatable in expectation for at least one player. That player that gets a higher payoff in the equilibrium of the relative payoff zero-sum game, that player then has a winning strategy, unbeatable expectation strategy. If the value of the game is 0, then both players have a strategy that is unbeatable in expectation. So coming back to what Jonathan was asking, in fact, this extension to mixed strategies tells us that we always, well, subject to the conditions that the game have in the Nash equilibrium, we actually always have an unbeatable strategy for at least one of the two players. So it actually helps to have an unbeatable strategy to look at mixed strategies. Right, so the results, I think may be useful to look at examples, but before looking at examples, what can be also useful is to try to determine which of the two players is the one that has an unbeatable strategy without calculating equilibrium of the game. if we can calculate the equilibrium of the game, that gives us the answer. But there may be use in actually trying to find which player has an unbeatable strategy without calculating the equilibrium of the game. And for this, what Amir et al. Papers also discuss is that one can look at what they call counter strategies. So strategy sigma I C, the counter strategy of player I against the given strategy of player J, sigma J. If this inequality holds, if player I can get a higher payoff than player J in expected terms, say. These counter strategies may be different for different strategies of player J. So it may be that player I can always find a strategy that is good in this sense against a given strategy of player J, and that can hold perhaps for each strategy of player J. And if this holds for each strategy of player J, then this is sufficient for player I to have an unbeatable strategy. Again, Amir et al. Paper say this for pure strategies. If the game has a pure saddle point, and player I has a counter strategy for each a pure strategy of player J, that is sufficient for player I to have an unbeatable-for-sure in their case strategy. For extension to mixed strategies, if the game has a Nash equilibrium and player I has a counter strategy for each mixed strategy of the other player, then this is again sufficient for player I to have an unbeatable-in-expectation strategy. And the proof again follows the intuition similar to the previous proofs. If we look at the equilibrium of the game delta, the relative payoff game, this is a zero-sum game, minimax is equal to maximin, if the equilibrium exists. And then this expression minimax actually means that player I has a counter strategy for, that player I has a counter strategy for each strategy sigma j of player j means that minimax is non-negative, which then implies that the value is also non-negative. Right? Because this tells us that for each sigma j, there exists sigma i that gives player I non-negative payoff. And then if we minimize over a set of non-negative payoffs, it still be non-negative. So that's why you have the non-negative inequality here. So looking for counter strategies may be helpful in identifying when players have unbeatable strategies. So here is the example that I promised to try to understand the concepts. So here is the game. Game gamma is this one. In fact, it's to start with, it's a very simple game. It is already a constant sum game. If we transform it to relative payoff game, then it's a properly zero-sum game with these numbers. Strategies, mixed strategies of the two players can be defined as sigma 1 for player 1 and sigma 2 for player 2 with p corresponding probabilities, p and q, the strategy 1 for the two players. Expected payoffs, we can calculate from game gamma. Expected payoff of player 1, it's these 2 and these 2 multiplied by appropriate probabilities. The other payoffs are 0. Same for player 2. And the difference between expected payoffs can then be written in this way. And then we can look at player 1's payoff, this relative payoff from player 1's point of view. For each q, we can maximize this relative payoff and find that it is for q smaller than 1/2, it is maximized at p equal 1, and it's non-negative. For q larger than 1/2, it is maximized at p equals 0, and it's non-negative. Therefore, we know from previous proposition that player 1 has an unbeatable expectation strategy. Of course, for this simple game, was an easier way to see it is simply to realize that half-half is an equilibrium of the relative payoff game with value 0, and therefore both players have an unbeatable expectation strategy here. But I nevertheless went through these steps to show that if the game is not that obvious, say this one, I modified the payoff of player 2 to 6 here instead of 2 before. Now this game is not constant sum anymore. The relative payoff game is still constant sum by construction. It's not that obvious what its equilibrium is, because it's not that difficult to calculate it, but it's not that obvious that it is half-half. Certainly half-half is not its equilibrium, something else. But we can again look at expected payoffs of the two players from game gamma, and the difference in expected payoffs rho is this expression. And now for some q, namely for q equals 2/3, the maximum of this expression is negative. If q equals 2/3, then we have that 8p minus 12pq cancel. So we have an expression that doesn't involve p, so we can calculate this as a constant number, which is negative. What does it tell us is that player 1 does not have an unbeatable strategy anymore, because q equals 2/3 beats any strategy of player 1. So player 2 has an unbeatable strategy in this game. And we can also check it with all the equilibrium calculations. For game delta, 2/3, 1/3 is in fact an equilibrium with this value minus 2/3 that I've just calculated. As a note, it is different from equilibrium of game gamma, which is this sigmas, sigma 1 and sigma 2. And what one can say even more in this example is that player 2 has in fact more than one unbeatable strategies. Any q that is around 2/3, between 1/2 and 3/4, is an unbeatable expectation strategy for player 2. Player 2, and there are actually more unbeatable expectation strategies than equilibria of the game. So hopefully examples help in understanding what concept tell us for each game. I have one more example of a symmetric game with 3 strategies. In a symmetric game, an unbeatable strategy is the same for both players, because when we transformed it into a relative payoff game, then the game is also symmetric. That is called the skew-symmetric games in some of the earlier game theory literature. And so game delta has a big equilibrium that is symmetric with 0 value for the both players. So both players has an unbeatable strategy in these situations. And this example, I try to illustrate that equilibrium of the game gamma, this one can be quite different from an unbeatable strategy concept. In this case, if epsilon is -1, for example, so that this payoff is actually 1 and -1, then it is strategy S3 that is unbeatable. while equilibrium strategy of my gay gamma by construction is S1 is nice payoff, but unbeatable strategies can lead to quite low absolute payoff to the players. Okay, so the examples to illustrate the use of the concepts. I have further examples that look at games from the literature and see what the unbeatability concept can tell about these games. Here is a foray into history of game theory and look at what is now known as culinary blotto game that was first discussed in Borel's paper in 1921. That is the original French language paper. In 1953, Econometrica published an English translation of it. So this game has two players, and players choose three numbers, x, y, z, non-negative, and sum up to a fixed amount. And the payoff of player I is defined by these expressions. It may not be transparent if you don't know this game, but what these expressions mean that if a player allocates these amounts in such a way that his amounts are higher than the opponent's amounts on two of the three numbers, battlefields, in culinary blotto interpretation, then the player wins. You cannot win all three, obviously, because you and the opponent has the same budget. You cannot allocate more on each of the three battlefields, your troops on each of the three battlefields, but you win if you allocate on two battlefields. You win these two battlefields, you lose the third one, but 2-1 is a win for you overall. So these expressions is what they're trying to say. So this game is symmetric, and it's also zero-sum already by construction. So skew symmetric game. Being a symmetric game, it has a mixed strategy equilibrium with value 0. And what it means then from all the previously discussed is there is an unbeatable-in-expectation strategy for each player. And I have here a quote from Borel's, from English translation of Borel's paper, where he talks about trying to determine a method of play that gives the player who adopts it a superiority over every player who does not adopt it. So it's not completely clear if he means a relative payoff comparison, but it looks there is something like that in this quotation. Borel also talks about a version of the game that involves integer amounts of x, y, and z. They have to be strictly positive integers from 1 to whatever number and sum up to a fixed number b. And for b equals 6, then this form of the game can be written in the normal form. This game can be written in the normal form. That's how it looks like. And in this matrix, if you look at it for a while, you may realize that strategy 2-2-2 is the one that doesn't have a -1 in its payoffs. So it guarantees the player who uses 2-2-2 at least 0 payoff, same as the other players, or sometimes winning payoff. So this strategy is unbeatable for sure for each player. And it's also what Borel discusses, and he mentions that 7 is the smallest integer for which the game does not have simple manners of play superior to all others. So for 6, b equals 6, it does. And b equals 5, it does. And b equals 4, it does. For 7 or more, sometimes it does, sometimes it doesn't. What we also know from what I talked about previously is that for any b there will be an unbeatable-in-expectation strategy, since the game is finite and has a big strategy equilibrium. So we can find an unbeatable strategies for these games as well.
So
So that is, yes. And
just going to thinking about the concept. So unbeatable strategies, there's something of spite effect in them, right? In the sense that you care
Mhm.
about yourself relative to other people, but it's ordinal, right? You care only that you do better, or at least as well as the others, but not by
Mhm.
how much. So
Yes.
there could be an unbeatable strategy that for any given things that other people do, it will be possible for you to increase the gap even more, but you don't care about that. You know, it might create a weakness elsewhere. So,
Yes. So, for example, in this case, in this example, as I mentioned, player two has many unbeatable strategies for
yeah,
any Q in this interval. I didn't calculate it directly, but I think the equilibrium strategy that has leads to the value minus 2/3 is probably the best in terms of what you described. So it gives
okay.
the player two guaranteed 2/3 more than player one gets.
I see. Yeah,
Other strategies would give player two more than player one gets, but they would guarantee probably a smaller amount than 2/3. I think. No, I didn't do these calculations, but I think that is goes towards what you're asking. So we can potentially select within the set of unbeatable strategies something that is the best unbeatable strategy in some sense, in the sense of maximizing your relative payoff. But yes, I'm not talking about the
yeah,
yes.
interesting. Thank you.
Okay, so I talked this. Then further a couple of examples I probably will talk about more quickly. Chronodopoly game, familiar to most of you, I expect. Two farms, choose quantities. There is an inverse demand function, decreasing, the cost function, that is weakly convex, and that's farm's profit. Now, if we take QIW to be such amount that makes price equals marginal cost, which can be called Walrasian output, then this strategy of producing Walrasian amount is the unbeatable-for-sure strategy for each firm. That was noticed already by Schaffer when he introduced the finite population evolutionary stability concept for linear functions. Then Begger-Redondo generalized this for more general functions, cost functions, and demand functions. But that is not something I do. So that's not something new, but it is another example of the game where previous concepts tell you what an unbeatable strategy is for players. Now again, if we want to compare it with the Cournot-Nash equilibrium of the game, then unbeatable strategy is producing a larger amount, a Walrasian amount. Here is for linear demand and cost. And there is a spite effect that unbeatable strategy would lead to zero payoffs for both players, while Cournot-Nash equilibrium, of course, leads to positive payoffs. A couple of more examples are the contests. I can also find unbeatable strategies in Talog contests with two players, because the Talog contests can be reinterpreted as a Cournot-Duopoly game with isoelastic demand function for the previous reasoning applies. And an all-pay auction where a player wins some prize with value V if player puts higher effort than the other player. There is no pure strategy equilibrium, and there is no pure unbeatable strategy, no unbeatable-for-sure strategy, but we can find a strategy that is unbeatable in expectation which is a uniform distribution of bits on 0 to 2v, value of the price. And again, this strategy would actually lead to negative absolute payoffs, but it guarantees 0 relative payoffs. Again, this spite effect. So I don't want to spend too much time on these examples because I want to move on to n-player games. In two-player games, we had that unbeatable strategies exist. In more standard games that we look at in economics. So here in n-player games, one can look at different concepts of what unbeatable means. What I talked about before was that player I would be better off, have a higher payoff than any player J, which can be also written as max here. On the other hand, one can also look at what I call unbeatable-on-average strategy player I, that would guarantee player I that player's payoff is higher than the average of other players' payoff or anything that other players can do. It is also equivalent to looking at average of the other players. This condition and these conditions are equivalent. For n equal 2, also the average and the max of one number also equivalent. So there was no reason to differentiate this for n equal 2, but for larger games, for more players, one can differentiate these concepts. And what then one can show that obviously average concept is a weaker concept than unbeatable beating every other player. Beating the average is easier than beating every other player. But even that is not sufficient to have existence anymore for n-player games. It's easy to construct a game. So here is an example which has no unbeatable on average strategy. And therefore also no unbeatable in expectation, no unbeatable for sure strategy. The similar concept to relative payoff game for two-player games was actually already mentioned by Shubik and Levitan, the so-called beat the average game, where one can look at the relative payoffs in terms of payoff of player I and the average of the other player. Looks like a reasonable generalization of relative payoffs for two players. Here is for n players. And so if we start with this game on top and construct its beat the average game here at the bottom of the slide, this beat the average game does not have a strategy that guarantee a player 0. These games are symmetric, so we can expect that the most player can guarantee him or herself is 0. But this game does not have such a strategy. And the reason, as I write in these bullet points, is that strategy S1 of player 1 will be beaten if both other players choose strategy 2. Superscript is the player, subscript is the strategy number. And strategy 2 of player 1 would be beaten if the other players choose strategy 1. If we all play S1, 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 two players move to S2, they get 1 in relative terms, but the player who stayed at S1 gets -2, so loses an average. And it's the same for the other strategy deviation. These coordinated deviations of the other players destroy the concept of unbeatability. We cannot have unbeatable strategies in n-player games by the definitions that I used. On the other hand, there are n-player games which have unbeatable strategies. One is built-around oligopoly with constant marginal cost. This is its description. The firm that chooses the minimum price then is the only one that sells anything at this minimum price. there are more than one, they divide the demand equally. So in this game, a strategy of setting marginal price, price equals to marginal cost, is an unbeatable for sure strategy. And we can use this counter strategy argument. We can look at all other players as a composite player minus I with certain payoffs that are the maximum of other players' payoff. And we can show that if you choose price equal marginal cost, your payoff is 0 of player I, but other players get either less than 0 if they choose lower prices, or they get 0 if they choose higher prices. So the maximum cannot be larger than 0. So you, as a player I, guarantee yourself at least 0. And that is more than other players can do. So there are games that have unbeatable strategies, also for n players. And I was trying to look how one can find sufficient conditions for games to have unbeatable strategies. And what I looked at is aggregate games. An aggregate game is such that payoff of player I depends only on player I's strategy and an aggregate A, where aggregate A is a function of all player strategies, for example, the sum or the average or minimum or maximum, some kind of aggregator of what all players do. I will look at symmetric aggregative games where the strategy sets are the same for all players. The aggregate is a symmetric function, and the payoffs of the players then also does not depend on the name of the player. If player chooses S and the aggregate is A, then it doesn't matter what name the player has, I or T. Cournot oligopoly, symmetric Cournot oligopoly is an example of such functions with the aggregate production as the aggregate and the profit function and defined as normal. So what then one can say is that in some classes of these symmetric aggregative games, there are unbeatable strategies. One class is where first the strategy sets are compact to have maximum or minimum in them. If the payoff function of players are such that it is either increasing in Si for each value of the aggregate, or they are such that they are decreasing in Si for each value of the aggregate A, then there exists an unbeatable for sure strategy for each player, since the game is symmetric. And the reasoning is that the maximum of this expression, payoff of player I, if the functions are increasing, then the maximum is at the maximum of the strategy space, which belongs to it because it's compact. If the functions are decreasing in Si for each I, then the functions are, the maximum is at the minimum, the strategy space. But since the game is also symmetric, we can also conclude that maximum, meaning that pi I of S star is larger than pi I of any S. But since the game is symmetric, pi I of any other S is equal to pi J for this strategy S. So if player J chooses something else, S, player will not get more than player I. Player I guarantees to be better than any other player. One example of such games where these conditions hold is minimum effort game, where a payoff function of a player depends on the minimum of what other players, all players choose. And the cost, for example, can be linear. Then the strategy A, the minimum of the available effort space, is unbeatable for sure for every player. More generally, if the payoff function is separable, has a benefit part that depends only on the aggregate, and the cost part that depends only on player's own strategy. For monotone cost functions, then it satisfies the conditions in the proposition. And a final content slide I think that I have is that if I look at aggregative games that have this property of submodularity between players' strategy SI and the aggregate, which is defined in this way, that such payoff function is submodular if this difference is decreasing in A for larger S choice. Essentially, this generalizes substitutability, which for differentiable functions defines in this way, that this cross derivative is non-positive. So modularity applies for functions that are not necessarily differentiable. Now, if we have an aggregative game that is symmetric with compact strategy spaces, the aggregate is the sum. If the payoff function is continuous and concave in S, strategy of the player, him or herself, for each value of the aggregate, and also submodular, then there exists an unbeatable-on-average strategy in this game. The reasoning is in these 4 lines. For these classes of games with compact strategy spaces, there exists a star that maximizes this expression, which is sometimes called aggregate taking behavior. It's equivalent to price taking behavior of firms in a kind of standard Cournot game, relation behavior of firms in standard game. What Alois Ferrer and Anya show is that this strategy S star that is aggregate taking then also satisfies this inequality. It's also generalized ESS in the sense of Schaffer. And that's what this inequality means. For this, submodularity is needed to show this. Now, if you take arbitrary strategies of other players and replace them with the averages. So instead of S2 up to Sn, which can be arbitrarily different, we replace them with all other players choose S minus 1, which is the average of these strategies. By construction, the aggregate is the same because the sum of these strategies is the same. But since the payoff function is concave, this inequality then holds. And that means that player 1 who plays S star would get more than this other player J that in this combination, which in turn is larger than this combination, which is the payoff strategies of all other player J. Player I then 1 has an unbeatable strategy as unbeatable on average strategy S star. Cournot oligopoly is an example of this game, of such a game. We can check that it satisfies concavity, payoff function in Q, satisfies submodularity, or differentiable version of submodularity. Valerian output, such where price equals marginal cost, is then generalized ESS. And from what I showed, is unbeatable on average then in this game. You can also note that there is no unbeatable-for-sure strategy for Cournot oligopoly. It's easy to show for linear cost functions. If one firm produces slightly more than Valerian output, but another firm produces less but more or less than the firm that produces more, then price becomes larger than marginal cost. And firm J that produces more then gets a higher strategy than firm I that stays at Q star. Firm I is not better than firm J. cannot guarantee that as a firm that you always have a higher payoff than any other firm. But you can guarantee that you have a higher payoff than average payoff of all other firms. Okay, so I think I have more or less on time to finish. It's my last slide, and then there may be more questions. So what I try to talk today is about unbeatable strategies that are based on the concept that you want to have a better payoff than other players, which may be relevant for evolutionary survival. And here is a cartoon that shows how it may be relevant, that you want to be that better than other player, not necessarily better than the bear. What I introduced, what I talked about is variants of unbeatability. Unbeatability-for-sure guarantees you higher payoff than other players for any realization strategies. It doesn't always exist, especially in n-player games. Unbeatability-in-expectation, you guarantee a payoff not lower than other players in expected payoff terms. This exists in finite two-player games. And for n-player games, I talked about unbeatability on average, that strategy that is not beaten by the average payoff of others. And try to find in what games that strategy exists. I think that unbeatable strategies can be seen as variants of evolutionary concepts in games and perhaps analyzed further. But for this talk, I thank you for your attention.
Okay, thank you very much. I'll just stop the recording.